Last time we started our exploration of various kinds of number theoretic and algebraic objects that are useful for cryptography, n, which is the multiplicative group of integers taken modulo n. And you'll recall that the definition of z star n is it's all the numbers 1, 2, up through n minus 1, whose GCD with n is 1. So all the numbers between 1 and n minus 1 that are relatively prime to n. Multiplication mod n. As a special case of that was z star p, for p greater than 2 being prime. This is that, well, since p is prime, all those numbers are relatively prime to p. So the order of z star p is p minus 1. We also looked at this idea of subgroups that are generated by elements. So if you have a cyclic group, actually any group, but for any h that's in a group G, we had this notation angle bracket h, which we've used before for encoding as a bit string, but I think once we have the context set here that we're talking about groups, then this won't be confusing. And this is the standard notation that's used in a lot of algebra textbooks anyway. So the angle bracket h is the set of elements that you generate by taking h to the 0, which of course anything to the 0 is equal to the identity under whatever the operation is for the group. So it's the set of elements that are generated by taking h to the 0, h to the 1, which is of course just h squared, h cubed, and so on, up through h to the L, where L is the order of h. And you'll recall that the order of an element in the group is the smallest positive integer such that h to that number gives you the identity. So h to the 0 doesn't count. It's the smallest positive integer. And we've been looking at almost entirely at finite groups. There are infinite groups, but for us, finite groups are the ones that are the most useful and most interesting and that we're going to focus on. Z star p, for example, is obviously a finite group because it has a finite number of elements. And what we observed was that, okay, well, of course, if you have a finite number of elements in the group, then the order of an element of the group has to be finite. And it is the case, we didn't actually prove this last time, but I said it and I wanted to repeat it. It is the case that if you take the set of elements that are generated by any particular element, say h, that itself is a subgroup of the group from which it came, G. So within any group there are subgroups, and subgroups you can think of as being like subsets of the original set of elements that make up the group. The operation is the same. So if you have a subgroup of z star p, it's a subset of the elements of z star p, where the operation is still multiplication mod p on that subset. And if something is a subgroup, it simply means that it meets all the properties of being a group, in addition to having its elements be a subset of the original set. So any set of elements that are generated by H is itself a subgroup of G. And then I mentioned, and I hinted at the importance of this really beautiful result from algebra called Lagrange's theorem. Probably some of you have heard of Lagrange from like Lagrange interpolation. Lagrange's theorem says that if H, capital H, is a subgroup of G, capital G, then the order of H divides the order of G. So the order of every subgroup of a group divides the order of a group. So in particular, the order of any element is going to divide the order of the group. Because if you take any element and you look at the subgroup that it generates, the order has to divide the order of the group, and the order of an element is nothing more than the size of the subgroup that it generates, right? So you can define this either way. You can either say the order of an element is the least positive integer such that the element raised to that integer gives you the identity, or you can say it's the size of the subgroup that's generated by H. Those are equivalent things, at least for finite groups. I'm not sure if it's true for infinite groups, but for finite groups, it's certainly true. So these were all things that we looked at last time. Lagrange's theorem is going to come back again today to be quite useful. We were motivated by looking at the Diffie-Hellman key exchange, and you'll recall the Diffie-Hellman key exchange, we'll come back to it later, is you have Diffie-Hellman key exchange over a cyclic group in particular, is given a group and a generator and the group order. Alice picks a number between 0 and the group order minus 1, called that x, and then she raises the generator g to the x, and she sends g to the x over to Bob. Bob likewise picks a y between 0 and the group order -1, and then raises g to the y and sends g to the y over to Alice. Then Alice takes Bob's message g to the y and raises it to the x, and because of cyclic groups, it doesn't matter how you do multiplication, so g to the yx is the same as g to the xy. And Bob likewise takes Alice's message g to the x, raises it to the y, and now they both have g to the xy. This is the basic classic Diffie-Hellman key exchange. And motivated by that key exchange, we established 3 computational hardness problems that are about cyclic groups. So the first one we looked at is the discrete log problem. And you'll recall that last time I said, if you take g and you raise it to the x, that's discrete exponentiation. The opposite, the inverse operation there is the discrete logarithm, just like logs and exponentiations are inverses of each other, like in the real numbers. The discrete log problem is given a g to the x. So we can look at it right here. You pick, so just think about this from like Alice's side of the Diffie-Hellman key exchange. Alice picks an x between 0 and n-1, which I've noted here, that set 0, 1, ... n-1, that's just the integers mod n, right? So zn. And I'm going to use that in the other definitions just for compactness. So Alice picks a random exponent between 0 and the group order -1. Then she would raise the generator g to the x and then send it to Bob, right? So now we're imagining, imagine that the adversary sees that first message from Alice, g to the x. So we give the adversary g to the x. It knows the group g, the generator g, and the group order n as well. That's all. It's part of the experiment, so you can just assume the adversary knows it. So the adversary gets g to the x, and its job in the discrete log game is to output an x prime such that g raised to the x prime is the same as g to the x. And we looked at last time the fact that if you have a generator for a group, so recall a generator means if you keep raising it to powers, eventually you produce all of the elements of the group. So a generator is an element whose order is the same as the order of the group. And we allow the adversary to output an x prime that could be different from x, because if you go around the cycle that we use to think about how x generates the group, how g generates the group, you can go around the cycle. If you start at the beginning, you can go actually anywhere you are. You can go at most the order of the group steps before you return to wherever you started, and so you can keep going around this cycle as many times as you want and keep returning to the same element. So in the discrete log game, we allow the adversary to output an x prime that could be different from x. It just has to be the case that g to the x prime lands you back at the same element as g to the x. If it can do this, then we say it has won the discrete log problem. In other words, it has found an x prime that's equivalent to x in the sense of taking the log of g to the x. Because recall that taking the log, in particular, it's the log base g of g to the x, is just finding x, right? So that's the discrete log problem. Given g to the x, essentially find x. So this is all well and good, but we were left with questions, computational questions, and security questions, frankly. So I want to go through some of those today. The first one is this: how does one find? So here let me use my zoom in here. Right. So here we go. How does one find a generator when the order of the group is large? This is the first question. It's easy. If I give you a small group, if you have like z star, 7 or z star 11, one of these very small groups, it's easy to find a generator, right? You can just try. You could just take each element. 1 is not going to be a generator because 1 times 1 is 1, so you're immediately back where you started. So it doesn't generate the group. But you could go through each of the elements and figure out what is their order. And when you find one whose order is the same as the order of the group, you have a generator. So for small groups, it's easy. But small groups are also not going to be secure for like the Diffie-Hellman key exchange, because if you think about it, if you have a small group, and maybe I'll leave this for you as an exercise, if you have a small group, finding the discrete log of an element is going to be easy. just again by just brute force. So you know that the groups are going to have to be large. And when I say large, I mean like groups whose elements can be represented with 512-bit strings. So numbers between 1 and 2 to the 512. So, big groups. In these cases, how do I find a generator? Well, okay, so let's look at a specific example. So here I'm saying, let's consider Z star P. So maybe I'll zoom in a little bit here. So here, let's consider Z star P for prime P of the special form that we talked about last time, these so-called safe primes. And we'll see why they're so-called safe primes today. We have a prime of the form P equals 2Q plus 1, where Q itself is a prime. So as a very small example here, 7 is an example. 7 is a prime of this form because 7 is 2 times 3. So here Q is 3 plus 1. So let's say that we have Z star P for one of these safe primes P. The possible orders of these elements, well, this is Lagrange's theorem is going to help us out here. What are the possible orders of the elements in this group? Well, Lagrange tells us because the order of an element has to divide the order of a group, this tells us then that the possible orders of elements are the divisors of the order of Z star P, which is P minus 1. So the possible divisors of P minus 1, in this case, if you think, what is P minus 1? Well, if you just move that plus 1 to the other side, P minus 1 is equal to 2Q. So the possible divisors are going to be 1, 2, Q, or 2Q, which is the order of Z star P. What that tells us then is that we need only to take an element and to find a generator, take the element. Of course, raising it to the 1 you don't need to bother with because that's just going to give the element back. So you can square it. If you take the element and square it and you get back 1, the identity, then it's not a generator because its order is 2. If that's not the case, then you take the element and you raise it to the Q. If the element raised to the Q is not 1, and you reach this far in the test, then it must be the case that that element is a generator because the only other possible order is 2Q, which is the order of the group. So the number of tests that you have to run is significantly reduced if you use a prime of the form 2Q plus 1. You really only have to do 2 exponentiation tests. I take my candidate generator, I square it. If it's equal to 1, I throw it out and start over. If it's not, I raise it to the Q. If it's equal to the 1, if it's equal to 1, I throw it away and start over. Otherwise, I know I have a generator. So you only have to do 2 atomic exponentiations, if you will. Element squared, element to the Q. Well, okay, this then raises the question of, let's say that I take an element and I square it. And I'm in a big group. I'm in a group where, as I said, the order of the group, so here we're looking at number 2. Let's say that the log base 2 of the order of the group is 512, meaning the elements in this group are represented by a 512-bit string. So this is a huge group. How are we going to compute? Say we have some element H that's a candidate generator. How are we going to compute H to the Q, where Q is this prime? And note in particular, Q is a prime in this giant group, right? And moreover, because Q is roughly P minus 1 over 2, that means you know that you probably have a big number, right? You at least have a number that can be represented in 511 bits, basically. So, well, the obvious way to compute H to the Q is just to do H squared, H cubed, H to the 4th, and so on. But if Q is a 512-bit number, you're not going to do all those exponentiations in a for loop. That's just going to take forever. So what we're hoping for is some fast way to do these modular exponentiations much faster than brute force. So the brute force way requires essentially that you do order of the group multiplications, right? You actually can do it in much faster. You actually can do it in log of the order of the group. Think about that. Order of the group is like 2 to the 512. Log of the order of the group is 512. So this is a massive savings. Here's how you do it. This is something called square and multiply. So let me maybe shift this over a little bit. So square and multiply works like this. Think of the integer q as a bit string. So think of its base 2 representation. So here I've written it out. You've got, bit number 511 times 2 to the 511 plus bit number 510 times 2 to the 510 and so on. It's just a base 2 representation of the integer q as a bit string. Square and multiply, let me show you by way of a small example here. So the small example is, imagine we've got q that is a 5-bit string, and it's the bit string where the most significant bit is 1, and then 1, and then 0, 0, 0. Well, the number that's represented by this is 17. So this is computing h to the 17, what we're doing. So imagine you start out, you have a 5-bit register, and it's initially all empty, and so the light blue zeros are positions that haven't yet really been touched by the algorithm. So you start out with this empty thing, and if you think about what's in the register right now, it's 0, right? So we have h to the 0, and that's 1. So at each step in the algorithm, what we're going to do is take what's currently in the register, shift it to the left by 1, and then load in the next bit in our string, starting from the most significant bit. So you begin, you have all zeros, and that's representing h to the 0, which is just the identity 1. All right, so the first step is you shift all those light blue zeros to the left by 1. It's not a circular shift, it's just a shift. And then you load in the first bit. Okay, well, so what have we got here? We've loaded in a bit 1. So now the intermediate number we have in the register is the number 1, right? Well, if you think about that, what are we doing? The actual, if we're thinking about like the exponentiation, what we have at this point is h, our candidate generator, raised to b sub 4, so the 4th bit, times 2 to the 0, because we've got a bit that's either 0 or 1, but it's in the position that would be 2 to the 0 if we're thinking about a base 2 representation of a 5-bit integer here. Well, b4 is 1, because our bit string is 1, 1, 0, 0, 0, reading from the most significant bit. b4 is 1. 2 to the 0 is 1. So what we've actually got here is h raised to the 1 times 1, which is just h to the 1, which is h. Okay, so now we repeat the process. We shift the register to the left, which means now the 1 that's in the least significant bit gets shifted to the next position to its left, and we load in whatever's the next bit in our bit string, which is a 1. So now what do we have? We have a base 2 representation of a number whose bit string is 00011. So if you think about what that means, now we've got, if we were to raise h to this number, we've got h to the b4, which is now moved into the 2's position, or 2 to the 1 position, plus b3, which is the bit we just shifted in, raised times 2 to the 0, which is just 1. So we've got 1, 1. And if you think about what's happening here, so of course, we've already, b4 and b3 are both have the bit value 1. So we end up with h squared times h to the 1. Okay, now this is important. This is where the square and multiply comes from. When you left shift in this register, you have to remember what we're doing is we are left shifting up in the exponent, right? When you left shift in a register, you're multiplying by 2, which I think probably all of you have seen at some point, but if you haven't, it's pretty obvious, right? If you left shift in a register and you're thinking of that register as being the base 2 representation of a number, left shifting is just multiplying by 2. Well, then if this is an exponent, you're squaring, right? The 2 is in the exponent. So you left shift, which is to say square whatever you currently have, and if you load a 1 bit into now the least significant bit of the register, that's the same as multiplying by the element h. So let me go through this again just to make sure it's clear. When we left shift the register, we are effectively squaring the element because we're left shifting in the exponent, and left shifting is multiplying by 2, so we're squaring. So we take whatever we had, we square it, and then we look at the new least significant bit in the register. If that bit is a 1, that tells us we actually need to multiply in h. And the intermediate representation in light blue on the right-hand side is trying to make that clear. This is the square and multiply part. Okay, so let's try it. The next move. So now we shift our register to the left by 1. What we actually have then is h raised to this summation here, b4 times 2 squared, b3 times 2 to the 1, b2 times 2 to the 0. And if you look at the bit values of b4, b3, and b2, that gives us h to the 1 times 2 squared, which is 4. What do? We just squared the h squared part that we had before, because previously we had h squared times h, right? So now we're squaring everything that we had before. So squaring h squared times h is going to give us h to the 4th times h squared. So we've squared that. And now we look at what's the least significant bit. Well, the least significant bit now is a 0. So that's b2 is a 0. So b2 is so we don't actually have to multiply in, because anything raised to the 0 is 1. So at each step in the square and multiply algorithm, what you do is you take whatever is the element that you have currently in your intermediate product that you're computing. You square it, and then if the next bit you're looking at is a 1, you multiply in the element. If the next bit you're looking at is a 0, you just multiply in 1. Square and multiply. And I think you can see, I didn't give you the final 2 steps, but I think you can see what's going to happen as you continue to left shift and move in. Each time you're going to square, and because the bits to the left are 0, you're going to just multiply in 1. Oops, better charge my Apple Pencil. I have to close it here, sorry. So when we square in, we're just going to keep squaring the elements that we have, and if you just work through the last 2 steps yourself, you'll see that what we're going to end up with is, of course, h to the 17, because we'll end up having, in the end, the string that we care about, which is 11000, which is 17. So we will compute in the end h to the 17, but because we're doing it via this square and multiply approach, the number of operations that you actually have to carry out, as I've shown here in yellow, is log of the order of the group, right? Because if you have a 512-bit string, the number of this left shift and load, which is equivalent to square and multiply, the number of those you have to do is just the length of the bit string that represents the exponent. But the exponent is representable in log the group order number of bits. So square and multiply gives us a way to compute exponentiations using log of the group order number of operations. The operations here being, left shift to, or effectively squaring and multiplying. So really, since squaring is just multiplying, it's just O of log of the group order number of multiplications is what you need, as opposed to O of the group order number of multiplications. So this is a massive savings, and it gives us a way to very, very efficiently compute large exponentiations. So that's a cool trick if you haven't seen it before. I will say that this is a way to do this, to do exponentiations in large groups. And as an algorithm, it's fantastic. There are some catches in practice, though, and we won't talk about these in detail, but I do at least want to make you aware of the fact that we've talked in the class a little bit about side channels, things that fall outside of the attack model that we capture in our security notions. Things like, our security notions capture things like if I ask a plain text, I see the corresponding ciphertext. It's treating things as a black box, right? All that's leaked by our oracle is the output of the oracle. But if you have a side channel attack where things are being leaked by our quote-unquote oracle that are outside of the attack model. So imagine, for example, that the oracle not only leaks the result of the computation, but also leaks how much power was used in that computation. If you look at an implementation of square and multiply on certain architectures, I'm not sure how general this is. It may in fact be very general, but if you have a 1-bit, so when you do the square, you always do the square, right? Because that's just left shifting, do that every time. But you can imagine that if you were trying to save time or power, when it came time to do the multiplication, if you see that you have a 1-bit, well, you have to multiply in the group element again. So you're going to use some time and some power in order to do that multiplication. if you see a 0 bit as the next thing you're loading in, you know that what you should do there is multiply by 1. But, multiplying by 1 is doing nothing. So maybe just don't do it, in which case it takes less time and uses less power. So square and multiply is susceptible to side channel attacks if you can distinguish the amount of power or the amount of time it takes as part of, if you know that a square and multiply operation is being carried out, and you can distinguish between the amount of time or power that it takes during the multiply step, then you could back out what the bit is. And of course that's bad, because if you can back out the bit, if Alice is using square and multiply to produce g to the x, and you can use a side channel to distinguish whether or not I just multiplied in something or I just multiplied in a 1, well, then you know the bits of x. So you do have to be careful when using something like square and multiply to make sure that your implementation is not going to leak the bits as a result of observing things like time or power. Okay, so that's two computational questions answered, which are, how do we find generators when the order of the group is large? We could just pick. You can either start from the beginning of the group, or you can pick a random element of the group, which for z star p is just picking a random integer, and then try this test of squaring it and then raising it to the q. Squaring it's going to be cheap. Raising it to the q could be expensive because q could be very, very large, but now we have a way to do h to the q for an arbitrary h in time that is linear in the number of bits needed to represent elements of the group. So that's 2 computational problems solved. So we're looking at these first 2 issues of how do I find generators? And we saw that for, in particular for z star p, where p is one of these safe primes, and we'll see why it's called a safe prime actually shortly. So when p is of the form 2q plus 1, we saw that all you need to do is take a candidate element and square it, and if that's not equal to 1, then you raise it to the q, which is a large prime. And if that's not equal to 1, then you know that your candidate element must be a generator, because the order of an element has to divide the order of the group. And then we saw, well, how do you do h to the q, where h is a candidate element that you're trying to see if it's a generator? How do you do this efficiently? You do it via this square and multiply approach that allows you to now do large exponentiations in log of the group order instead of order of the group order operations. Well, okay, so how are you actually going to, pick which element to try as a generator? One obvious idea is you just pick a uniform number out of z star p. So that's basically just picking a random integer between 1 and p minus 1. And in fact, you don't even have to pick 1, right? Because you know that 1 is not going to be a generator. So you just pick a random number between 2 and p minus 1, and you do these 2 exponentiations of squaring and raising to the q, and that's your test. Well, if you're going to do it randomly, then you'd like to know, well, how many times do I expect to have to sample an element and test it before I find one? And this, there's a question here that's directly related, which is, how many generators are there in a cyclic group? And so to answer this question, this is a side note, but to answer this question, I want to introduce a really important number theoretic function that's going to come back when we talk about RSA, and that is something called Euler's totient function. Now, Euler's totient function, or phi of n as it's typically written, it's the size of z star n. You can take that as a definition. So in particular, phi of p, when p is prime, is p minus 1, because that's the size of z star p. Okay. So there's a particular property that's useful, particular multiplicative property about Euler's totient function that's very handy, and I want to introduce you to it by way of example. So let's look at z star 15. So the elements of z star 15, recall, are the numbers between 1 and 14 that are relatively prime to 15. So that means we're not going to have any numbers. 15, the prime factors are 3 and 5. So none of the numbers between 1 and 14 that have 3 or 5 as a factor will be in this group. And so that leaves us with 1, 2, 4. Of course, not 5, not 6, because they obviously are not relatively prime to 15. 7, 8, 11, 13, and 14. If you go through these, you'll see that these are the numbers that are in this z star 15 group. Well, phi of 15 is the size of z star 15, which if you count them up is 8. But then you also notice that 8 is equal to 4 times 2. And 4 is phi of 5, because phi of a prime is p minus 1, 5 is prime, so 4 is equal to phi of 5. And 2 is phi of 3. And 5 and 3 are the prime factors of 15. So what you get here is that phi of 15 is equal to phi of 5 times phi of 3. And in fact, in general, this is true. If you have distinct primes p and q, then phi of p times q is equal to phi of p times phi of q. It has this nice multiplicative property. And this is in general. Okay, so that's a little side note. In a cyclic group, it turns out, we're not going to prove this, but it turns out that the number of generators in a cyclic group G is phi of the group order. So in particular, if the group is Z star P, then the number of generators is phi of group order. Group order is phi of P, just by what we said a moment ago. So the number of generators is phi of P. Well, phi of P is P minus 1. We just established that. So the number of generators in Z star P is going to be phi of P minus 1. And we could stop there, but if we're using one of these so-called safe primes, and as I said, we'll see why they're called safe primes in a moment. If you're using one of these where P is equal to 2Q plus 1, then P minus 1 is just 2Q. And by using this multiplicative property, we can say that phi of 2Q is the same as phi of 2 times phi of Q. Well, phi of 2 is just 1. So the whole thing is just Q minus 1. Phi of Q is Q minus 1. That's the number of generators in Z star P. And if you look at it, well, the order, the entire size of Z star P is P minus 1, which is 2Q. So if Q is big, the whole group is of size 2Q, and the number of generators is Q minus 1, but that's roughly Q. So that tells you that roughly half of the elements of Z star P are generators. So if you want to pick a random generator, you just expect it in 2 samples, 2 numbers. You'll find one via our efficient generator finding test of squaring and raising to the Q, and using square and multiply to do these. You now have a way to find a generator very quickly, a random generator very quickly. Expected 2 samples. Okay. Right, so moving on to point number 3 of this lecture. How large should the group be that we're going to use? Well, we'd said earlier that if you think about the Diffie-Hellman key exchange, you at least have to have it be the case that if you see g to the x, you can't recover x efficiently. In other words, it has to be the case that whatever group you're working in, the discrete log problem has to be hard. That's necessary for security. Because if it's not, well, we already saw how you can attack, right? So we are going to need groups that are large enough that the discrete log problem is hard. Now, I said earlier that if I give you a small group, you can solve the discrete log problem just by brute force. It's not hard. So intuitively, we know the group's going to have to be big, but how big is the question? Right? Brute force is one kind of attack, but maybe there are much better attacks, and we'll need to make the group large enough that it's going to be hard for those better attacks to win in finding the discrete log. And what I'm about to show you is something called the giant steps, baby steps algorithm. And this is an attack that works on any cyclic group. So it's a generic attack on a cyclic group for finding discrete logs. It works on any cyclic group given a generator for it, which means that we're going to have, when we analyze it, we'll see that this attack takes roughly square root of the group order, space and time, which is going to tell us that the group's going to have to be large enough that square root of the group order is a number that's too big to be feasible. I want to stress that this is a generic attack, meaning it works on any cyclic group. There may be cyclic groups for which there are even better attacks, but we know that we're at least going to have to make a group large enough to avoid things like this giant steps, baby steps algorithm. And as we'll see, it turns out that all generic attacks for finding discrete logs, for finding discrete logs in cyclic groups are going to take roughly square root of the group order. So let's look at the giant steps, baby steps attack. So we're going to start, we have this parameter t. And actually I see that I've made a small typo here. I'm going to fix it really quickly. Oops, let me get my eraser. We're going to call this y. little y. Sorry for the notation clash from before, but hopefully it won't be too confusing. All right, so we've got this parameter t, and we're going to set t, our parameter, to be equal to square root of the group order. And we'll see why momentarily. Okay, think about the discrete log problem. Find you're given a g to the x as input. And here I'm calling it y. So we're given g to the x as input, and you want to find x. So this attack exploits the fact that you can write x just using basic arithmetic. You can write x for any fixed t. You can write x as k times t plus some remainder that's between 0 and t minus 1. And this is basic arithmetic. So we're going to fix t to be square root of the group order. And what we're going to do is we're going to make two lists. The first list is going to be giant steps. So I've got on the left-hand side here this sort of visual representation, and on the right-hand side I've got the two lists. So the first thing we're going to do is we're going to divide. Oops, I see I've forgotten something in here. Let me add a little marker. This is not going to be to scale anymore, but you'll get the point. We're going to divide the circle up into sort of, if you will, t-sized chunks in the exponent. So we'll mark the circle with g to the t, g to the 2t, g to the 3t, and so on, all the way around. And when we do this dividing up, we know we're only going to have up to the very last marker before we come back to the identity of g to the 0. Before we come back to that, is going to be this marker here, this one. This is the last one we're going to have. Because what happens, if we were to go, the next one would be g to the t squared in the exponent. But t is the square root of the group order, so t squared is just the group order. So that's what I've got here in this magenta right here. T squared is the group order squared, or square root of the group order squared, which of course is just the group order. And g to the group order is 1 because g is a generator. In fact, because of Lagrange's theorem, anything to the group order is going to be 1 because the order of an element always divides the order of a group. But specifically for a generator, the group order is the smallest power that you can raise it to, the smallest positive power that gets you back to the identity. So we only have to go our last exponent, if you will, in this list, if you started from g, is going to be this g to the t minus 1 times t. So that's a list of size t, has t elements in it. So it takes us roughly square root, since t is square root of the group order, it takes square root of the group order time. Let me zoom in here and fix this notation. Not square root of g, but square root of the order of g. This list that we made so far is size t. Yeah, it has that many elements in it. These are our giant steps. These are our markers we're going to do. And then what we're going to do is we're going to do our baby steps list. So we're going to start with the element y, and that's the first one. That's g to the x by definition, just above. And I've marked where g to the x is on our circle. So it's here in magenta, right here, between g to the kt for some value of k and g to the k plus 1 times t. Right? It's in there somewhere. It's this dot right there. Now, our baby steps list is basically going to take that dot and move it clockwise, one small step at a time. So we'll take y. We take y times g, the generator. Well, since y is g to the x, then y times g is g to the x plus 1 in the exponent. So it's a small step. Yeah. And then we do it again. We multiply in g again and again and again. Each time what we're doing is we're moving a little bit, right? Because we're going from g to the x to g to the x plus 1, g to the x plus 2, and so on. We're going to keep making these tiny steps. What you notice is, eventually, we're going to hit this marker g to the k plus 1t. We're going to hit that marker. And we'll know that we hit that marker because as we're generating these values in the right list, y times g squared, and so on, eventually, we're going to hit something that's in the left list. When we hit such a thing, we're done. We now have a way to find the discrete log. Why is that? Because if we hit this g to the k plus 1 times t, well, we know what k plus 1 times t is because we picked t, and we have this list, so we know exactly where we are. We know what the exponent is at that marker. So we just take k plus 1 times t, the marker that we hit, and we go backwards the number of steps that we had to go in our baby steps, and that gives us exactly g to the x. So the giant steps, baby steps algorithm gives us a way to find the discrete log of g to the x. In particular, it finds x using square root of the group order space to make the left list, and time, at worst case, to basically making the right list. You don't actually even have to keep the right list, right? You can just start with y, and then if it doesn't hit anything, you go to you go to y times g, and you check that, and so on, right? So the complexity, the search complexity, is actually going to be, can be much more efficient because you're not even like keeping that space, and you're just looking through this list. So if you have an efficiently searchable structure, you actually can search in time less than square root of the group order. But overall, the time to make the list and the time to search the list, you can just take it as bounded by O of square root of the group order. So what this is telling us, as we said earlier, is that your group has to be large enough so that square root of the group order is too big in terms of time and space for any reasonable attacker to carry out. So that tells you you're probably going to need groups whose order is like, 2 to the 512. In order to, you could even get away with maybe slightly smaller than like 2 to the 256 is the group order. So a group whose elements are representable by 256-bit strings, maybe that's fine. But as I said, this is a generic attack. So there may be attacks in your particular group that are better in terms of their efficiency, which means you're going to have to make the group larger, but at least you're going to have to make your group order large enough to defeat the giant steps, baby steps generic attack. It's actually a little bit worse than this for us because there is an ancient result called the Chinese remainder theorem. And I'm not going to tell you all about it, although I do recommend that you go look it up and see. It's really pretty cool. But effectively what it does is the following. It says, if you have a group, a cyclic group, you know its group order, you can look at it as one giant circle like we've done here. But the Chinese remainder theorem gives you a way to map from the big circle that I've drawn here to a bunch of small circles where each of those small circles is directly related to the primes that are in the prime factorization of the group order. So for example, if you take z star 15, the order of that is 14, and the prime factorization is going to be 2 times 7. And so the Chinese remainder theorem says, okay, you can map bijectively, so back and forth between the big circle, which has 14 elements on it, and two small circles, one that has 2 elements and one that has 7 elements on it. And it has the property that this mapping is not only invertible, but anything that you do on the small circles, you can map that back to having done the same thing on the big circle. So in other words, you can solve the discrete log problem on the 2 small circles and then efficiently map back to what the discrete log would have been on the big circle. And so the combination of CRT, the Chinese remainder theorem, plus the giant steps, baby steps algorithm says your group order, when you take its prime factorization, if you only get a bunch of small primes, that says you're going to go from one big circle to a bunch of small circles. And on small circles, you can solve the discrete log problem quickly via the giant steps, baby steps algorithm, because again, it's square root of effectively the size of these little circles. And this is why safe primes get their name, because if your prime p is of the form s times q plus 1 generically for small s, let's take s be equal to 2 because that's what we've been looking at. If your prime is of the form 2q plus 1 for a large prime q, then the group order is p minus 1, so its factorization contains only the factors 2 and q, which means via the Chinese remainder theorem, you go from a big circle of roughly size p, where p is a big prime number, down to a very small circle of size 2 and a large circle of size q. In fact, the size of the circle that's related to q is going to be effectively the same size as the original big circle. And now the giant steps, baby steps algorithm remains difficult because you still have to solve discrete log on a big circle, square root roughly of the size of that circle, which if you've chosen 2q plus 1 as your safe prime expression, the size of the q circle is going to be essentially the same as the size of the p circle, so it still takes roughly square root of the group order to do. So safe primes are called safe primes because they are ones in which it's still hard to mount this generic attack. And this is the case in general. All the generic attacks for finding discrete logs on cyclic groups are all roughly square root of the group order complexity. And once you roll in the Chinese remainder theorem, it tells you in order to keep that, you need to make it so that you use a safe prime, p times q plus 1 for a big value of q, big prime q. Okay, so that is a generic attack for finding discrete logs, and it helps to guide us to know how big of a group should we make. And in particular, it's telling us, okay, if you're going to use Z star P as your cyclic group, you should use one of these safe primes for big prime Q. And so now the number of bits you need to encode the big prime Q needs to be something like 256 or 512 in order to remain secure against the giant steps, baby steps algorithm. All right, so we've addressed questions of finding generators and how to choose primes if you're going to use Z star P, for example, as your cyclic group, how to choose primes so that you remain secure against the giant steps, baby steps, or related algorithms, which is a generic discrete log finding attack. So this tells us, okay, good. So if you're going to use Z star P and you've chosen the safe prime, so prime of the form 2q plus 1, you're at least secure against the generic discrete log finding attacks. This still raises the question of whether or not using Z star P is for safe prime P is in fact a good choice for doing like the Diffie-Hellman key exchange. Because all we've established so far is, structural things aside, that we know how to choose a prime so that we are secure against discrete log finding attacks. But discrete logs, the hardness of discrete log is only necessary. It's not necessarily sufficient for security of the Diffie-Hellman key exchange. So the question is it in fact the case that Z star P with a safe prime is a good choice for doing your key exchange over? And the answer is it depends. It depends on what it is you want to assume as your hardness property for this group. It's probably safe to assume discrete log is hard as long as you've chosen the prime, the safe prime, to be large enough. But, is that going to give us what we want? And the question, I say it depends. It depends because it depends on how you're going to use the cyclic group. So if you're going to use it to do Diffie-Hellman key exchange, then you might have one answer. If you're going to use a cyclic group to build the public key encryption scheme, which we're going to see how to do in the next lecture, then you may have a different answer. So the answer is it depends. And let's see why it depends. So we've said earlier that for a random exponent x and a random exponent y, we know that both g to the x and g to the y are uniform in Z star P. Why? Because g is a generator for that group, and x and y are uniformly random exponents. So you get like a random position on the circle that you'd get when you use g as a generator. So the question is, given that you have a uniform g to the x and a uniform g to the y, is it the case that g to the xy is uniform? Why is this interesting? Because if you look down at the bottom, so you look down here at this picture, you remember that our straw man security notion for key exchange was that we want that the key that's generated. So we had this notion of like, okay, the adversary sees g to the x, which is a uniform group element. It sees g to the y, which is a uniform group element. And then Alice and Bob can compute g to the xy. And the security notion said that g to the xy ought to be indistinguishable from a random key, right? So if you take g to the xy, represented as a bit string appropriately, that should look like a uniform random bit string, at least to any computationally efficient test. So this is a meaningful question to say, well, if g to the x and g to the y are both uniform in Z star P, is it the case that the key that's generated is itself uniform in Z star P? And this is why I say it depends, and this question is interesting. So we're going to see, in fact, the answer is no. And this may be surprising, because if you have two things, g to the x and g to the y, that are uniform, it seems maybe like g to the xy should be uniform as well. So let's consider, as a way of seeing that the answer to this is no, that we're going to look at, if you have a uniform element, then anything that's true about uniform elements, should hold for all the uniform elements. So let's consider the following set. This is the set of elements H that are elements of the group. So this is just a generic result for the group. In fact, maybe I should fix this because it's not just the group we're talking about. It's actually, whoops, wrong implement. There we go. So let's take H in Z star P. Z star P. Okay, so let's try this again. We're going to consider the set of elements H that are in Z star P such that there exists for that H an element Z that if you square Z, you get H. In other words, this is the set of all elements of Z star P that have square roots. Right, the square root of H in this case, Z, would be a square root. So this is the set of things that have square roots. Okay, so let's look at an example of this. So here we've got, maybe I'll zoom in on this. Here's Z star 11, and I've got here this mapping up top. I've got the elements of Z star 11, which are of course just the numbers 1 through 10, and then I've got squaring. So if you square 1, you get 1. If you square 2, you get 4. If you square 3, you get 9, obviously. If you square 4, 4 squared is 16, mod 11 is 5. 5 squared is 25, mod 11 is, you can take out 22, so that's 3. And then, so I've written those in this magenta color. For the others, it's actually helpful to start from the back end, so you start from 10. Well, 10 is the same as minus 1, mod 11. Right? 10 is the same as minus 1. So minus 1 squared is just 1. So if I square 10, I'm going to get 1. And if you would just want to do it the long way, you can do it that way too. And if you continue this way, what you get is this pattern just sort of mirrored. And so the result of this is that the numbers in the bottom, these are the numbers that have square roots. In particular, 1 has square roots 1 and 10, which you'll notice are plus and minus 1. 4 has square roots 2 and 9, which you notice are plus and minus 2, and so on. Squaring is a 2-to-1 map, and so in particular, this is telling you that the elements 1, 3, 4, 5, and 9, the numbers that appear in the bottom here, the distinct elements that appear in the bottom here, these are the numbers that have square roots. And the numbers that have square roots in Z star P they have a special name. These are called the quadratic residues, modulo P. Here in particular, it's for the P equal to 11. But these are the quadratic residues in the group Z star 11, or these 5 elements here. And more generally, the quadratic residues are written as typically QRP. Well, so as I just pointed out, you notice that, maybe I can get rid of this box, that Z star 11, well, 11 is actually an example of a safe prime, right? It's 2 times 5, so our Q is 5 plus 1. The order of Z star 11 is 10, and the size of, I can't really say order yet, but the size of QR11 is 5, which you notice is half of the size of Z star P. And in general, this is true. The size of the quadratic residues is going to be half of the size of Z star P. And it's actually the case that I haven't said this, but the quadratic residues are themselves a subgroup. So they are a subgroup of a particular size. And if you've chosen a safe prime, what you notice is from this example that 11 was a safe prime 2 times 5 plus 1, where 5 is our Q. The quadratic residues have size 5, and they're a subgroup. So the quadratic residues are a subgroup of order 5. More generally, if you're using a safe prime, these are going to be the subgroup of order Q, where Q is a large prime. So the quadratic residues make a subgroup whose order is prime. That's different than the order of Z star P. Remember, order of Z star P is P minus 1, which is definitely not prime, because P minus 1 for primes bigger than 2 all the primes are odd, so p minus 1 is even. So p minus 1 is definitely not prime. But Z star p does contain a prime order subgroup called the quadratic residues. And this is going to be important shortly. But let's continue with this. So in general, we have this this property that the quadratic residues are half the size of Z star p. And moreover, you can show that, in fact, if you take a generator G and you raise it to the A, G to the A is a quadratic residue, meaning it's a number that has a square root, if and only if A is even. The if part's easy, right? If A is even, then that means you can write as A equals 2 times K. Well, if you have 2 times K in the exponent, that means you can just write that as G to the K squared. So it's clear that if you have an even exponent, you do have square roots. The other direction you can show as well, it's not hard, but the point is that G to the A is an element that has a square root if and only if A is even. Okay, so let's look now at G to the X, right? So if we ask for a random X, think of the Diffie-Hellman key exchange, the probability that G to the X lands in the quadratic residues, meaning G to the X has a square root, well, if half the elements have square roots, G's a generator, you've picked a uniform exponent, that means you're picking a uniform element of the group, half the elements have square roots, so the probability that G to the X lands in the quadratic residues is a half. And likewise, the probability that G to the Y lands among the elements that have square roots is also a half. Now let's look at G to the XY. Well, I just told you you have this if and only if that the exponent has to be even in order to have a square root. So the probability that G to the XY is in the quadratic residues is, well, 1 minus the probability that it's not in the quadratic residues. And you're not in the quadratic residue if x times y is odd. When does that happen? It happens if and only if both x and y are odd, right? Because if either of them is even, you get an even product. So really what we're interested in, what's the probability that x is odd and that y is odd? But if you take the numbers between 1 and p minus 1, or equivalently 0 and p minus 2, half of those are even and half of them are odd. And because x and y are sampled independently, the probability that either that x is odd is a half, the probability that y is odd is a half. So the probability that G to the xy has a square root is 1 minus a quarter or 3/4. Hence, it can't be the case that G to the xy is uniform, because with probability 3/4, it has a square root. And it should only have probability a half of having a square root if it was uniform. So what this tells us is, if there is an efficient set membership test for the set QRP, in other words, if there's an efficient square root finding test in Z star P, then it cannot be the case that the decisional Diffie-Hellman problem is hard in Z star P. Why? Think about it carefully. If you have an efficient test for telling whether or not something has a square root, then it won't be the case that G to the xy, remember the decisional Diffie-Hellman problem, maybe it's actually useful to go back very quickly and look at it. The decisional Diffie-Hellman problem says you get G to the x and G to the y, which are uniform group elements. And you get either G to the xy, which with probability 3/4 has a square root, or you get G to the z for a uniform z, so that's a uniform group element, and the probability that G to the z would have a square root is a half. So in one case, if the challenge bit is 1, you have an element that has a square root with probability 3/4. And in the other case, if the challenge bit is 0, you get an element with probability a half has a square root. So if there is an efficient square root finding or an efficient set membership test for, is this an element that has a square root, then that gives you an efficient way to distinguish between G to the xy and G to the z. So if there's an efficient square root finding algorithm, or an efficient test, it doesn't even have to find the square root, just an efficient test that says yes or no, this element has a square root, then it can't be the case that the DDH problem is hard in Z star P, and in fact that is the case. There is an efficient test for finding for determining whether or not something has a square root in Z star P. If you want to go look it up, it's you're computing the Jacobi symbol, and in fact the Jacobi symbol is closely related to Fermat's little theorem, which is a test that you use for primality testing. It's a really interesting sub area. But the punchline is there is an efficient test, in particular because we have this fast square multiply. The test basically becomes like, give me your element, I raise it to the power p minus 1 over 2. If I raise it to that power and I get back a 1, then I don't have a generator. If I get back a minus 1, I do have a generator, roughly. So the point is that given that we have efficient way to do modular exponentiation, which we do because of square and multiply, there does exist an efficient test for having a square root, which means the DDH problem is not hard in Z star P. And this is why I said a moment ago, should you be using Z star P with the safe prime P? Well, and the answer is it depends, because if the thing that you're building on top of Z star P needs the DDH assumption to hold, so in particular, if the thing that you're building needs for G to the XY to be indistinguishable from a uniform group element, then you should not use Z star P, because the DDH assumption does not hold in Z star P. If you need something less, if you need just the CDH assumption, which says you can't compute G to the XY given G to the X and G to the Y, then you're probably safe. But there are fewer things that one can do starting from a group in which you're assuming only the CDH assumption holds than you can do in a group where you're assuming the DDH assumption holds. So what should you do if you have Z star P? You need to build something out of this cyclic group Z star P where you need G to the XY to look like random. What you do is, in fact, is operate not over Z star P, but over the quadratic residues. Why? Because you can show that if the group that you're operating over has prime order, this is why I stressed this a moment ago, if the group that you're operating over has prime order, then it will be the case that G to the XY is essentially uniform. It's a very small deviation from uniform. And so if you look at specs, for example, for things that are using Diffie-Hellman, or they're using Diffie-Hellman hardness assumption is somehow the underlying assumption, you'll often see them not tell you explicitly, but they'll say, oh, pick P needs to be a safe prime, and then you need a prime order subgroup of Z star P, and then you actually do your Diffie-Hellman over that. Well, okay, if you pick a safe prime, then that's telling you that the order of any element, the order of all the subgroups, must be either 1, 2, Q, or 2Q, if your safe prime is 2Q plus 1. And Q itself is a large prime number, and the quadratic residues are a subgroup of order Q. We just established that a little while ago. So therefore, the quadratic residues are a prime order subgroup, and you can do Diffie-Hellman key exchange over the quadratic residues. The quadratic residues are actually also a cyclic group. There are generators for the quadratic residues. It's not hard to find them, following roughly the same steps you've already outlined. How do you find a generator for the quadratic residues? Well, you take a random element and square it. And that gives you an element for sure that's in the quadratic residues because it has square roots, because in particular one of the square roots is the element that you sampled randomly before you squared. So that element squared is in the quadratic residues, and then you can say, okay, what are the possible, how do I know if this thing's a generator or not? Well, you again use Lagrange's theorem, because Lagrange says, if you take any element from the quadratic residues, what are the possible orders of that element? Well, the order of the quadratic residues is Q, where Q is prime. So the only possible orders are 1 and Q. So finding generators is exceptionally easy in the quadratic residues. Essentially, just pick a random element of Z star P and square it. And then that becomes your G that you use in the Diffie-Hellman key exchange. All of the operations are the same as before. When you take G to the X, you're still doing multiplication mod P, because again, the quadratic residues are a subgroup of Z star P, and subgroups are just small, like subsets of all the elements, but you still use the same operation. So all the operations remain the same. Square and multiply works the same, all that kind of stuff. It's just now you're operating over the quadratic residues. You do this because the quadratic residues have prime order if you've chosen a safe prime P. The prime order is large, which means in particular that discrete log finding algorithms are going to be quite complex. And moreover, the DDH assumption can be assumed to hold in groups of prime order. And you can look this up if you like. But G to the XY, if you're working over a cyclic group of prime order, is statistically, not even computationally, but statistically close to uniform. So, to summarize all that, if you want to do Diffie-Hellman key exchange, or if you want to do anything over a Z star P, whether it's building a public key encryption scheme, as we'll see in the next lecture, whatever, the safest bet is to pick a safe prime for P, and then actually choose a generator for the quadratic residues, and then operate over the quadratic residues. That's the way you should do it. Okay, so that's today's lecture. Coming up in the next lecture, we're going to introduce public key encryption as a syntactic primitive. We'll see that it's not going to take us long at all. A few small changes from the symmetric setting. And we may even introduce the privacy notion for public key encryption, which is going to be called, again, IND-CPA, and it's going to look very similar to what we've already done in the symmetric setting. And once we've done that, once you've introduced public key encryption as a syntactic object and introduced a security notion, we can then talk about how one actually builds public key encryption schemes that are IND-CPA secure if one starts from a group in which the DDH assumption holds, for example, the quadratic residues modulo P. We'll also see how one can do it given only that the computational Diffie-Hellman problem holds. So if you're operating in Z star P instead of the quadratic residues, but there we're going to need an extra twist. We're going to need to do some hashing. And in order to get everything to work out properly in the security proof, we're going to have to operate in the random oracle model, which is where we're going to treat the hash function as if it's perfect in some sense. It's a publicly available random function. So we'll do all that, introduce PKE, introduce IND-CPA for that object, build stuff from DDH and CDH, and we'll also introduce the ROM. That's all coming up in the next lecture or two.